Hello, everybody. So part two, final part of when we started on Monday morning of understanding various aspects of AdS3 CFT2. So last time, I basically covered less than a third of what I thought I was going to cover. So I'll be speaking a little bit more quickly today for better or worse. I just want to kind of, I will be skipping a lot of I won't be doing many derivations. I will just basically be trying to do things that I think are crucial so that I can get to the punchline. But if I feel that I missed explaining something in a lot of detail, I'll incorporate it as a homework so you can have a little bit more context about oh, what does it mean to show something, or what was that part meant to be so that it gives it a little bit more cohesiveness. So, but in any case, still interrupt me, ask me questions if it becomes extremely obscure and incomprehensible. But I don't know. I really want to at least get to the very end, so you know what this is all about. But okay, so the previous lecture, just very quickly, so where we ended was basically here. It was a condition on the spectrum of the CFT, such that we would have we could reproduce the entropy of the black hole. And the last thing that I want to do in this context is talk about why this is the case and how to phrase it a bit more generally. So I just wrote it oh, I want to be able to have the Cardy regime and this extended validity range. But there's a nicer way how to cast this as a condition on the spectrum of the CFT. It's a more workable condition, and it gives some insight on how the CFT spectrum will be organized. And by that, we're going to look at the perturbative spectrum. So as we started on Monday, we had in mind that the classes of theories that we wanted to consider, that we wanted to study, were theories that at low energies, when G Newton goes to 0, were basically well described by the Einstein-Hilbert action plus some matter. And now I want to discuss a bit more, what are we assuming about this matter contribution? Okay, so we described a bit the classical phase space. We noted, oh, there's AdS as a solution. It's a maximal symmetric solution. There's a BTC black holes. They're going to be also the boundary gravitons, the Brown-Hanaud states. Everything, we basically showed how everything was organized in terms of representations of the Virasoro algebra. But let me refine a little bit more what we expect out of this as an effective theory. So it's nothing too deep or complicated. You can phrase it quite simply. So the point is the following. So, okay, so what are we assuming about the matter contribution? In general, any perturbative contribution to these computations. So what we were interested in, so this matter, one thing that I'm going to assume is that, so we're looking at the behavior of the system at finite beta, at finite temperature. And from this point of view, in this classes of theories, if you have these Brown-Hanaud boundary conditions and you don't put any VEVs on the matter contribution, and you also don't allow it to have any type of sort of source turn on for the matters, because that otherwise will tell you that it's not at finite temperature, but also at some other finite chemical potential. So if I'm only considering the system at finite temperature, the matter will always be something that will look like wrinkles on top of the black hole. So you will have the black hole as a solution, you will have thermal AdS as another solution, but everything else just comes as little wiggles on top of those two things. And so your expectation from when you're computing a gravitational path integral, roughly speaking, I know Tom has been telling you more about what we are learning about the gravitational path integral, but to the level of today, what we're expecting is that this, okay, so we usually say this should be some integral over the space of metrics, some path integral of the space of metrics, path integral over the space of field configurations of your action, your 3D action, I guess with a minus sign for these fields over here. And usually the way that we organize this is like as a sum over saddle points. Each of them weighted by their classical contribution, which is the leading part, is the part that we usually discuss. So this will be the value of the action when you're satisfying the equations of motions. But then there's as well corrections to this. So there will be like, so if this goes like 1 over g Newton, then there's going to be a 1 loop correction, for instance, and more around each saddle. And this 1 loop correction will basically be of order g to the 0. Okay, so it will be something that is independent of g Newton. So these little wiggles don't scale with g Newton. So then the dominant part is this one, and then there's a subleading. The first subleading part is basically a 1 loop contribution that counts basically the oscillations of these fields around this background. And then you can have further like corrections, higher loop corrections that are even further suppressed. But from this point of view then, what we basically, there's expectations on how this behaves because it shouldn't scale with g Newton. So this basically tells you that the number of fields also that you have here, so as you're summing all the contributions and all possible configurations, you're saying nothing should scale really with g Newton. This should be always the dominant contribution, just the classical value of the action. So if I'm a little bit slightly more precise, let me just say, like, let's say that you have, for instance, just a vacuum contribution. You will also have the black hole, but just to illustrate what's happening. So there will be one of these saddle points will be the vacuum. And what I have in mind is that the vacuum will have its energy, which was C over 12 times, minus C over 12 times beta. So become plus. And then there will be a sum here over basically the energy configurations. This basically wiggles around global AdS that will look like this. And there will be more crap here. And this is the part, this is like the perturbative part that we're restricting. Okay. And this part is independent of basically in this language that I'm using here. So remember that C is basically measuring Planck length. This part over here is something that is of order C to the 0. Okay, so it doesn't depend on the central charge. So how does so usually how does this look like? So for example, how do these perturbative contributions look like? So the thing that always universally comes in as you're organizing this path integrals are, for instance, the boundary gravitons. So these are basically when you act with L minus N, let's say now that I'm doing the vacuum state, like on the vacuum, well, you can act with many of them, not just one, but they're basically the descendants that are coming from your Virasoro algebra that Brown-Hinot told us. And the perturbative contribution from this boundary gravitons as a function of beta, this is a result of John B. Maloney and Yin. They actually did explicitly this 1 loop computation. And it looks like what you're familiar in CFT2s is basically roughly like the eta function. Here I'm just writing it as a finite beta. So I'm not putting, if I had tau and tau bar, it will be 1 minus q times 1 minus q bar, but trying to keep it easy. But this is basically the eta Dedekind function with with the L-1 state removed. And roughly, if you look from here, so there's no C dependence here. So the number of descendants that you have, even in a CFT, doesn't depend on the central charge. Well, if the central charge is bigger than 1, it doesn't have explicit dependence on the central charge. You're just counting descendants of the Virasoro algebra, and it doesn't depend on C. But from the point of view of the number of states there, so if you tell me, okay, so how many states you have, this is bounded, and it basically, it will go like the square root of the energy of each of the states. And this is because the eta function is roughly, it's almost a modular form. So basically, if you have, what I'm approximating here is when the energies are very big, but just note that E is not something that is scaling with the central charge, okay? It's order 1 relative to the central charge. So these states never have like Planckian energies, okay? Now, you can also, I placed in the homework the case if you just have a massive scalar field. So it's written above what the partition function was. So this is just a one-loop determinant of a massive scalar field on AdS3, and then the growth of states was e to the 2/3. I'm going to bet if I ask you guys, ladies and gentlemen, to raise your hand, who showed this? Raise your hand. No, let's see. Did anyone raise their hand? Let me look at the participants. Nobody's raising their. Okay. For later, you can show that it goes like e to the 2/3. Basically, you have to relate the one-loop determinant to the McMahon function, and that allows you to see why you get a growth like that. But okay, in any case, that's how a massive scalar field goes. Again, it's independent of the central charge. But more generally, as a good string theorist, we usually have in mind that these theories of AdS come from a compactification. So in general, like you can think that you have a theory of AdS3 times some manifold M that I will denote that has dimensions d-3, so the total number of dimensions is d. If both of these guys have the same size, so if this has size L, and this also has some size L, so they're both equally big. So an example will be like AdS3 times S3, which is a solution of type 2b supergravity. It's like the favorite case we like to study. So an example is when you just have S3. What we expect there, again, from these compactifications and the way the Kaluza-Klein spectrum organizes themselves, like you will have some number of states defined by basically the characteristic of this manifold. But if you think of this as a whole, like what do I have here? I have an AdS times an MD-3 manifold, both have size L. So this is roughly behaving like a box of size, of dimension D, of some size L, okay? So from this point of view, what do you expect of what you could do in terms of like fields inside of a box of dimension D? Well, you would expect that it's free energy just from dimensional analysis, and what you learn in statistical physics is that the free energy of the system should just scale like F to the T to the D. And then if you tell me, okay, so then what are the number of states that you have in the system as a function, basically what is the entropy that you would associate to this? Again, this is all just dimensional analysis, but it will be the exponential of some numerical factor that will depend a little bit on the details of the geometry, but just in terms of the scaling, this will just go like in the exponential of e to the d minus 1 over d. Okay, so even if you have like more extra large dimensions, if you're doing just basically QFT on a box, this is the bound. So that's all I have in mind, that I'm bounding basically how many states I have because of like, yeah, just how many fields I can, how many oscillators I can fit inside of a box, okay? And so this gives us basically a condition on what we expect on the low energy. So this examples basically tells us what are the expectations of a low energy effective field theory of gravity, which is, yeah, there's no revolution happening in the statements that I'm saying here, but basically the expectation is that the logarithm of the number of states should be bounded by e to some power gamma, where this number gamma is less than 1, okay? So you can see from this expression here that this power here, no matter how many dimensions I put, even if I take d to infinity, the power up here will never exceed 1. It will asymptote to 1, but it won't exceed it. And so usually the requirement that you would have is like, okay, if you have some effective field theory, sorry, some effective theory of gravity in 3 dimensions, this should be your bound. Now, and this is for states. So this is an asymptotic formula where E is very big again, but the energies of these states are not scaling with G Newton, okay? Now, the thing that is really interesting about this is that it correlates really well with the discussion that we had about the black hole. So the condition that we wanted to have a black hole for which it had an extended Cardy regime is very much tied to this bound that I'm putting here on the spectrum. And so one of the things that this paper that I was referring to above, this HKS, so Hartman, Keller, Stoika paper, which I put as a reference on the Slack workspace, what they showed basically is that if you wanted to have this picture that at leading order, so as you write down this gravitational path integral, that the 2 dominant saddles were basically, so here you would have put the contribution from the BT set and the contribution from the vacuum. So the assumption that these are the 2 leading contributions in this expansion in G Newton, they basically showed that in the CFT, so if you wanted the CFT2 spectrum to behave as C gravity of beta. They phrase it as a condition for a phase transition, but roughly it's basically that. They basically showed that the states in the CFT at what we will call here light states, actually, they showed that a necessary condition actually was that this had to be basically just bounded linearly by E. So it's a little bit even more generous than what I wrote above. So here I'm actually requiring that gamma is less than 1. HKS tells me you could still have this picture if you allow this to be linear. But I don't want linear behavior because actually this is very characteristic. So this is a statement again. It's for the same regimes here. So it's for E of order C to the 0 and very big. So this includes gamma equal to 1, but I don't care about gamma equal to 1 because this is very characteristic of what we will denote below as a Hagendorn growth, which is associated to a string spectrum. So we know that if I get just an exponential growth of states, this is not going to be like some low energy gravitational theory. If it really grows exponentially like this, I'm going to have like more like a string description. But what's interesting, what these gentlemen showed here was that even if you have a string spectrum, you could meet this criteria of having an extended card imaging. But I want to avoid it. I don't want to have this as a feature. Okay, so cases with gamma equal to 1, I don't care about. Other people do, but I don't. And that's my choice. Okay. So round 2. Oh, sorry, no, this was round 1 because it's finishing, sorry, this part of the discussion, is that what I'm then going to define at this level of the discussion and what we've been doing. So my definition of what a holographic CFT2 is, so the set, so some necessary conditions are.
Can I ask a question?
Yes, someone is talking.
Yes. So when counting the density of states, you didn't assume that it was like you didn't assume anything from gravity, right?
Which density of states?
So that d of e goes as e to the power d minus 1 over d. It's general for any QFT, right?
Yeah, this over here, I didn't really, this assumes like nothing. Well, I assumes like.
Yeah, so for gamma is less than 1 for any QFT.
Yeah, yeah.
Okay, thanks.
I really didn't like, yeah, there's no, it's, I don't know, that the Hamiltonian is bounded, maybe like something like something like natural that you will assume as well in Stepnik. Yeah.
Oh, thanks.
Yeah. Yeah, but it's basically the extensive properties of like the thermodynamic behavior. So yeah, so what I'm assuming, if you want, is that these coefficients are not dictated by G Newton. That's the thing that is important for this, that these things are not going to scale like G Newton. So that assumes that, in particular, that the number of species is not growing with G Newton, which will be bad because then it will violate the fact that I can approximate the theory at low energies by the Einstein-Hilbert term. So, okay, so very good. So then what I'm requiring, this is just basically a recap because it will come, in what follows. So the number 1 condition that we had was that the central charge, which is 3L over 2G, is very big. So this is like the number 1 condition that you find. And then this, so this is 1. And then number 2 is that if you look at the states that don't form a black hole, that this is basically bounded, that they can grow exponential, but the power of that exponential gamma, I want it to be less than 1. And here, these are states that are basically order c to the 0, very big. So this is a condition. So this, these 2 conditions, so this is the large central charge condition. I decided not to. Okay. Don't care. Okay. Then this one I decided to close. Fine. So this condition over here, there's a jargon for it. So this is what's called very sparse. Very sparse spectrum. And the reason why we call it very sparse is because the guys up here call this a sparse condition. And so since we're putting something stronger, we are like, okay, so we don't want, so this usually goes by the name of sparse spectrum. And so if we write it as in the box below, then it's very sparse spectrum. Okay, and if you impose these two conditions, if your CFT meets this criteria, then basically you're going to be guaranteed that the black hole entropy will be accounted for. So it's basically this extended Cardi regime. Okay, great. So that concludes the first part, the gravitational part of this lecture. And so, good, I have two necessary conditions of what defines a holographic CFT. Now let's go build the CFTs that meet this criteria. That's the name of the game. Okay. So, part two. Let's talk about our strategy. So how can I find, so the number one question here is basically, so how can we find CFT2s that obey 1 and 2? That's the name of the game. So I want to build explicit conformal field theories that meet this criteria. Great, so that if you wanted to do that, it kind of means, well, it actually, it does mean that if I draw a big circle here, it means that that ideally, if I wanted to answer this question, it would be great if I knew what the space of CFTs were, right? Because if I knew what the space of conformal theories are, then I can just be like, okay, let's go one by one and let's check which of them like meet the criteria, right? And so if I knew the space of conformal field theories in 2 dimensions, then I could like basically go and cut the space and decide, okay, some subspace of that space of conformal field theories are going to be holographic. And then you will tell me, okay, out of all this conformal field theories in 2 dimensions, the one that have a large C limit for which the spectrum is very sparse are this set. That will be the dream. One day, I hope one of you writes a thesis where you tell me what the answer to this question is. Okay, so if you don't know what to do for your PhD, here you go. Tell me what the space of conformal field theories are, and then identify the holographic ones. No, please don't. Well, try, but if your supervisor tells you to do this, that person is kind of masochistic because it's a hard question. Okay, so the point is that this is a hard question, but we can make progress. So what do we know about the space of conformal field theories? We do know things, so it's not like we're completely ignorant. So for instance, like things that we know is that we know that in the space of conformal field theories, there are free theories. I'm writing them here in the green region because free theories are not holographic. They don't satisfy the very sparseness condition. So if you have like n bosons and free scalars, and you take n to infinity, you would say, that's a large CFT, but it's not very sparse. So there's basically, the light states have an n log E-type growth that it's very problematic because then it tells you that this part that is perturbative still depends on n, and it basically doesn't meet the criteria that I was, it doesn't have the behavior that I was writing above. We also know, for instance, that there's a theory called Uvio. That's a very nice theory, and it has like an improvement to it, which is Toda theory. These are theories that also can have very large central charges. The problem is that the vacuum state is not invariant under SL2. There's also parts of the spectrum that are continuous, so they don't quite meet what I expected from this theory of AdS3 gravity. I thought that you couldn't do holography with them, but like all these nice things that I was describing above, no, it doesn't. Okay, it doesn't work. You can do it, like they're interesting for other reasons. Then there's going to be, there's also as well if C is less than 1. So if I have small values of central charges, there's minimal models. So they form like their little island by themselves. So these are kind of cute. But they have small central charges. So these are very nice. They're unitary theories. They have discrete spectrum. You know everything that you need to know about them. They're like the most integrable theories. But yeah, they have small central charge. So they don't work for my purposes. And there's more examples as well. I could keep on writing all day, like some like spots in this space of theories. There's as well extremal CFTs. I don't know, you can add to this list. This is not an exhaustive list, but there's all the coset constructions, WCW models. Oof, you can go on forever, but it's a kind of like I just want to illustrate that there's a little bit of a patchy knowledge of like what is understood about it. And so one of attempts, a research program that tries to do this as an aside, it's not something that I'm going to discuss, but if you're curious about attempts to understand what the space of CFTs is, you should look into the literature of what's called nowadays the Modular Bootstrap, which is an attempt to try to kind of quantify the space, try to discover new theories by imposing some consistency conditions on CFTs. But we're still far from understanding what the whole green region is. Okay, so this is where I'm going to. So I'm still. I'm still stubborn, and I'm like, yeah, but I still want to know what that purple region is. I want to kind of understand a little bit how it behaves, how many theories fit. Like the sizes here mean nothing, by the way. So I don't know how big this purple region is relative to the green region. Who knows? We don't know. We don't know. Okay. And so. But I want to have some grasp on it. We want to have some intuition to understand really what is the mechanism behind AdS3. How does it work? When does it work? There's all these interesting questions. And so in my attempt to try to describe the purple region, we will start imposing basically restrictions. So I'll make some compromises. So I'll compromise. And in that set of compromises, there will be some sacrifices. So I'll sacrifice some things. I think I'm spelling sacrifice correctly. And then, but there will also be, what I hope by the end of today is that despite the things that I sacrificed, there will be some gains. Okay, so there will be some new things that we're going to learn, although I kind of am going to like restrict to the set of theories that I'm going to be studying. So, okay, so how am I going to sacrifice myself in this program? So as a string theorist, you say, okay, it's always good to know, there is one example, or well, depends on how you count, but like there's like one very well-known example of how AdS3 CFT2 was first realized, is basically the D1, D5 system, which will show up a bit again. But what we decided to do as we were trying to understand how this question is like, okay, let's put on a little bit our string theory hat, and let's try to see that example that you tend to learn about when you're doing a string theory class looks super specific and looks kind of difficult to generalize, and you're like, oh, that's just very special to that D-brain system. But it wasn't obvious to us. It wasn't obvious to me. And so I'm like, okay, let's see if I can kind of mimic some of those features by looking at kind of keeping some of the key properties, but then modifying some other properties. And in that context, that's where we decided, okay, we're going to look at a class of theories that are called symmetric product orbifolds. And this is also where I'm going to make a compromise in the context of this lectures, because I'm not going to explain in full detail what symmetric product orbifolds are, because otherwise I will be speaking until midnight. But okay, I'll give you a cartoon of what these classes of CFTs are. So it's a very nice and simple way how you can start increasing the central charge. So let's say that you start with one theory. No, let me try again to my inbox. I can do better, I promise. Okay, perfect. Okay, so let's say that you start with one theory. Let's call that theory C, capital C, okay? That lives on a two-dimensional surface, okay? And so now let me grab that theory and repeat it. And then let me repeat it again. And let me repeat it again. And let me repeat it again. And as many times as you want. So I'm just tensoring the theory with itself lots of times, okay? So let's say that you have some n number of copies here, okay? So we start with a seed. So I'll be referring to the first one, the seed theory, that I'm calling C, okay? And then we tensored it n times. But I want to do something more than that. So just tensor it if I just do this. So if this guy had a central charge C, then this will have n times C. So I'm increasing the central charge by making many copies of it. So similar to oh, you have one scalar, it has central charge 1. You have two scalars, it has central charge 2. So, okay, you keep on repeating the theory a bunch of times. But what I want to do is something that is similar to gauging the theory. It's a version of gauging the theory in 2 dimensions. What we're going to do, because this is going to give us too much crap that won't meet this sparseness condition, is that we're going to mod out by the permutation, well, by the symmetric group. So I don't care in which order these theories are placed, okay? So you will mod out by this. So this defines for you the construction that is called symmetric product theory. So the resulting theory that we'll call Cn is basically the tensor of the n copies modded out by Sn, okay? And the resulting theory will have a larger central charge. So with central charge, basically n times C, where little c here is the central charge of the original theory. Okay, so this is a really, really nice way of basically increasing the central charge. Okay, so you know one theory, then you can build more theories by just repeating. Okay, now the other nice thing about this construction is that this is a theory, so we're imposing conditions on the spectrum, right? So the two conditions, well, sorry, the first condition was that I wanted large central charge. And then the second condition is a condition on the spectrum, right? It's a condition on how this light part of the spectrum, the states that have energies that don't scale with the central charge, basically what is a bound on them. And so as we're trying to solve this conditions, you also want to know about the spectrum. And this type of constructions, one of the advantages is that you have control, analytic control on the spectrum of Cn. Okay. So in general, like if you tell me, okay, start with a partition function for the theory C, and let's say that the partition function for that theory C basically has some Fourier coefficients dn times q to the n. So this is the partition function of the seed. Then you can basically say, so there's two things that you can do. Well, you can just write explicitly what the partition function of the symmetric product is in a not very illuminating way, but okay, it is what it is. So it's 1 over the order of the group times the sum over basically, so this order folding is basically allowing for all boundary conditions, either twisted or untwisted sector boundary conditions for the fields on the torus. So that's roughly what you're doing. And you're imposing different boundary conditions that I'm calling G and H, where G and H are elements of the permutation group, okay? So that's formally what the partition function looks like. But this formula, we're never, ever going to use it, because actually what you can do is you can build a grand canonical partition function that actually shows very, very elegantly how to get all the information that you want. So if you decide to sum over theories, so basically consider summing over n, so starting from n equal to 0, you're going to sum with coefficients Cn times p to the n, where p is, it's this variable tau that I'm writing here. I'm sorry, and q should write it up there. Q for the purposes of today is just e to the 2 pi I tau. So it's a function of rho and tau. This thing has a beautiful expression that's actually very nice to use, which is that it becomes a product formula. Sum over n for m positive where the powers in this product formula, so this d's here are the same as the d's there, but it's just that the entry is m times n, okay? So this shows you explicitly how, if you know the information about the seed, so if you know what these d's are, then you can just basically read off, you expand and p this product, and then you read off what the p to the n power is, and that tells you what the partition function of the symmetric product is.
Sorry, Alejandra?
Yes.
What was SN?
It's a permutation group.
Okay. Thanks.
No problem.
Yes, excuse me. In 5 minutes or so, maybe we can take a break and some questions.
Okay. Good. Time flies. I have said nothing. Okay. No, it's fine. Okay. Second half is going to go even faster, but okay. But okay, so let me just, so this looks beautiful. The name of this form, like, so, and I'll add the references on Slack. This is basically the digraph Verlinde formula. Basically showed that for symmetric product orbifolds, the grand canonical partition function had this beautiful product expansion. And this is what's actually useful and we will use, because I don't want to, this kind of looks a little bit more obscure here. It's kind of pretty simple how you read off. Like, I don't have to be thinking about what are the elements of the permutation group. So anyhow, so this is what we're going to do. We're going to be looking at this object here. Now, there's a big problem, though. There's a huge problem on all this, what I'm saying. So basically, what I have achieved is that I achieve at characterizing some family of large C CFTs based on a seed, which is great. I have this last formula that I have here basically tells you everything that you need to know about the spectrum of the CFT. But I love writing this in big red letters and with exclamation points. There's a there's a problem. I was hoping that I was going to be able to show you this, but I won't. And the problem is the following. So if now from the product formula, so now you would be interested in, so let's say you want to now understand. So the question would be, okay, now, so what you're interested in is understanding the behavior of these coefficients for the nth product. So the holographic condition is a restriction on the n sub n as n goes to infinity, and n is not scaling with big N. And the problem is that one of my collaborators, Christoph Keller, basically showed that as you take that limit, this d of infinity sub n, he showed that this guy's always grow like this. So I just decided to study the empty set. So this is Hagendorn growth. And it looks pretty bad. So, because I just told you that I didn't want Hagendorn. So what am I talking about here? This sounds like garbage. So this is Hagendorn. Which is very reminiscent of like, this is why like this type of pictures appear a lot on string theory when you have like, you kind of can be a bit crude. It's not quite like this, but it looks like a stack of D brains-ish, quote, quote. And basically these like brains, if you want, or well, these copies of these theories are not talking among each other. So I'm basically just counting excitations. If you want, you're counting just like strings among these like different n copies. And this is why you get like this kind of like Hagendorn growth. So they're like weakly coupled strings that are moving just around like these copies. And so that's why you get this exponential, like intuitively, like I'm being super like hand wavy, but if like the intuition here is that the only thing that I did is like copy a theory a bunch of times and not make the copies really talk to each other that much. And so it just gives you like some floppy strings kind of like among them. So that's what you get. So it looks like I'm wasting your time. So, and so with that positive note and outcome, and like, what is she going to say next in the next hour? Maybe let's now take this break and see if there's more questions.
Okay, good. Thanks. Are there any questions here on Zoom? Otherwise, there are some on Slack.
I'm sure I made many people upset.
I have a question. So are these DMN the BPS spectrum?
No, this is the partition function. I'll talk about the BPS spectrum so that I actually have something interesting to say. But yeah, I'm just saying, I'm assuming that these coefficients D are positive.
Mm-hmm.
That's what goes into this proof. So if you assume positivity, so this will be true. If and only if the D sub n's are mostly positive. You can have some minus signs, but basically that they're not, that there's what people call, there's no cancellations. So it's not an index, it's the actual total number of states.
Mm-hmm.
So
they don't need to be integer or any integrality condition is imposed.
Well, this is an asymptotic growth. I am assuming that, well, the proof doesn't assume integrality, but in general, like we do expect that these things are integers.
Mhm.
Just and if the seed, so in particular, something that you can show quite, and it comes in this DBV construction, if these guys are integers, then these ones are also going to be integers. And we expect that, yeah, like my starting point is a CFT where the partition function, where this is some number of states, and as such, it's an integer. But yeah, technically speaking, the proof of this doesn't assume integrality. It assumes positivity, that the coefficients are not trivial, or not too many of them are trivial.
Okay, thank you.
Okay, maybe then I can take a question from Slack. So can you clarify on the reason for Liouville and Toda theories not being holographic CFTs?
The vacuum is not invariant under SL2R. So, and in gravity, the vacuum state is basically global AdS. And global AdS has six killing vectors, 2 copies of SL2, which forms SO2, 2. And in Liouville, you don't have such state. So it's a problem, because then I don't even know how to map global AdS to a state in Liouville. That, yeah, and then there's a part of the spectrum of Liouville that is continuous, which, okay, you could like maybe account for, but yeah, the number one problem is yes, that you don't even know how to map global AdS.
Okay. There was also a question to clarify if the purple region of these holographic CFTs that you drew, these are CFTs with this very sparse spectrum.
Yeah. So there are
yeah,
CFTs that basically that obey 1 and 2. So let me write it here just to be clear for posterity. So at the level that I'm discussing now, so as I have defined what a holographic CFT is, it's basically condition 1 and 2. So I'm interested in knowing what are the conformal field theories that obey 1 and 2 as necessary conditions. It might not be sufficient, but yeah, it's the conditions that we're going to start imposing.